Okay, good morning, everyone. Can you all confirm if you can hear me clearly, right? Okay, so I want to welcome you to another statistics class. Of course, today the focus is going to be on introduction to linear algebra. Um, we're actually going to work on linear algebra because mathematics actually provide us with foundation to work with multivariate data, and that is a behind any statistical methodology lies mathematical theory, and that's why we'll actually want to walk you through some basic algebraic fundamentals are very, very applicable in multivariate analysis. So the focus of the week entirely going to be on that. And of course, today uh, I'm actually going to achieve the basic definitions and basic calculations. And then on Wednesday, it's going to be on matrix decomposition. And of course, on Friday, it's going to be on miscellaneous topics. Okay, so we want to start with basic definitions. And let me tell you this, we don't do math for fun. There's a reason why we do math. Okay, so like I said, mathematics is very, very essential, particularly when you're talking about algebra, linear algebra, you know, uh, with regards to our application in multivariate analysis. Okay, even though I know we are you're going to use software, but without, I think they actually program something behind the scene that you don't see. So, which is formula. Without formulas, of course, software is not going to work. Okay. Now, I want to start with basic definitions. Okay. So, in the basic definitions, um, we're going to talk about a vector. Okay. When you take a look at what I'm showcasing right now, okay, so that's a vector. Okay. Uh, you can see a one-dimensional array. We have A1 up to AN. Okay. And don't forget, in the multivariate analysis, where you work with so many features, okay, you could talk about vectors of means. Vectors of means. Okay. We normally have that. I mean, we have it in that kind of, that is the way it's going to look like. Now, um, we, if you take a look at another one that I want to show, okay, the n by p matrix, okay, that you are actually seeing right now, uh, that is more or less a replica of what we normally see in multivariate data structure, where you will collected observations, you collected several variables on observation. Okay, so it's going to be in form of a matrix. Okay, the breakthrough in multivariate analysis can actually be attributed to the knowledge in mathematics. So particularly the matrix algebra. Okay, now I want us to pay attention. We can have a matrix, and a matrix has a full rank, and we could have a matrix, and it doesn't have a full rank. Okay, now the rank of a matrix can actually be defined as the number of independent rows, okay, and the numbers of independent columns, okay. As you can see here, I said is the number of linearly independent rows. The rows have to be linearly independent, okay, and the columns as well have to be linearly independent. Okay, so if the row is linearly independent, we actually gonna call that a row rank. If it is linear, if the column is linearly independent, you're actually gonna call that a column rank. So the moment we have a column rank, a row rank, of course, we can actually say we have, you can define the rank of a matrix A. So in multivariate analysis, particularly when we are dealing with linear regression, where we want to estimate parameters, we expect our design matrix to have a full rank, because without full rank, of course, there is no way we'll be able to estimate the inverse, because we need the inverse of a matrix. But as time goes on, I'm actually going to unfold that. But what do we mean by a matrix having a full rank? If I have a 2 by 2 matrix, okay, it's going to have a full rank if the rank is 2. If I have a 3 by 3 matrix, it's actually going to have a full rank if the rank is 3. A 4 by 4 matrix, of course, it's going to have a full rank if the rank is 4. Now, if you take a look at this, I said we say A is full rank if rank A equal the minimum of n comma p. What is n? What is p? N is going to be probably the number of observations, and p the numbers of features. And of course, you have n arranged in a row, and you have p arranged in columns. Okay, so the rank of the matrix is going to be the minimum of that. What does that mean? Situation where you have a rectangular matrix where m are not the same, then if the matrix is going to have a full rank, then the minimum of the two. Does that make sense? That's what that means. Now, if n is less than p, what does that mean? If n is less than p, if the number of observations is less than the numbers of features. But here, let me first look at this in terms of having a row and a column. Okay, I said when the let me do this so that you can actually see what I'm talking about. Now, when you take a look at that, if n is less than p, okay, the full rank implies full row rank, and the rank of A is going to be equal to n. Okay, in this regard. So we have a full row rank. Okay, and of course, if n is greater than p, okay, the full rank implies a full column rank, and the rank of that matrix is actually going to be p. Okay, so these are kind of I'm actually going to say norm. Okay, but I'm going to demonstrate this to you now. Okay, if I have a rank A in this case, they can look at the rank A, and if you look at the dimension of this, don't forget n is actually, if n is the row and maybe p is column, you can see here the numbers of row and the numbers of columns are not the same for this particular matrix. I'm actually referring to this guy. Okay, they are not the same. Okay, but there's something you can actually investigate. Okay, you know, we before we can have a matrix can have a full rank, we said the column shouldn't depend on each other. Like, we should have a linearly independent, okay, and the row should not also depend on each other. But I wanted to start our investigation to see whether that is going to happen in this case. Take a look at this guy. If I multiply 1, if you look at the first column, let's do this. If you look at the first column, 1, 2, 5. If I do something to first column, and it automatically give me the second column, then they are linearly dependent. But what the rule says is that they should be linearly independent. Now let's take a look at that. If I multiply 3 by 1, that will give me 3. If I multiply 3 by 2, that will give me 6. If I multiply 3 by 5, that will give me 15. So which means the second column is depending on the first column. Okay, and that was what led us to having this. Take a look at that. Okay, so which means the second column is a multiple of 3. If you take a look at what I have, because of the fact that there's a violation of linearly independent, we're actually going to make a conclusion that that particular rank is not going to be a full rank. So before it can be a full rank, okay, they shouldn't have what I call, relationship in a way that we can determine a column from the other one. Okay, now if you come back to the next one, take a look at this one. Okay, and you're actually going to see that even though if you look at the first one, 3 times 1, 3 times 2, but 3 times 4 is not 15. Okay, so because of that, there's no violation as far as this is concerned when it comes to determining a full rank. Okay, now, and if you take a look at the next one, because we cannot write summation bjaj, okay, equal to that unless we set bj equal to 0. Now, whenever you see something like that, okay, let me circle that. Whenever you see this, that guy means for every j. For every j. Okay, so this guy, for every j. That's what that guy means. That notation means for every j. Okay, for every j equal to 1, like mean b, if you have a b1a1 plus b2a2 plus b3a3 and so on equal to 0. If you cannot write that, of course, that is that. Okay, now we want to go into transpose. Now, you may not necessarily know the reason why we actually talking about the rank, the transpose right now until we start something that is our application. Okay, so these are kind of things that we do when we have data set, even though we're making use of software, but they've been kind of programmed behind the scene. And why am I trying to show you all this is because uh, what is permanent. Let me just say that we find ourselves in a world where things are changing, and we want a situation whereby the model we're going to use will commiserate with reality. Okay, if things are changing, if you understand the mathematics behind the scene, then you will be able to bring out a change in your model. If you know what is programmed, you'll be able to know how to the mathematics involved in the modification of your model. And that's why we're doing all this. We can't rely on software because the software only work, only for what has been programmed. And at times the formula program may not commiserate with what is happening now. And that's why we are actually always going to have a way to do research because things are changing. Okay, now we want to talk about transpose. Transpose is more or less okay. If I have a row, I should convert a row to column, or if I have a column, I should convert column to row, and I can find the transpose of a vector. I can also find the transpose of a matrix. Okay, now let me tell you this. Whenever you add vector in multivariate analysis, we normally, that's what we use to describe several means. If you have a matrix, okay, your mind should go to variance, covariance matrix. Okay, variance, covariance matrix. A variance covariance matrix is not going to be a vector. Okay, actually going to have represented as a matrix where the column, the diagonal of the matrix will be variances, and the off diagonal will be covariances. But right now, I actually have a vector written as this, and I want to find the transpose of that. The transpose is converting, the column to row or the row to column. If you take a look at what I have, and let me also tell you this: if the dimension of A initially was n by 1, and by the time you find the transpose is actually going to change as well 1 by n. Does that make sense? Now, and that's also applicable to matrices. Okay, now when you have a matrices arranged in row and column, take a look at this guy now, and the dimension is n by p. Okay, the dimension of A is n by p, and I want to find the transpose of that. Finding the transpose of that, element in the row will actually be converted to column. I'm just going to show you something really quick. Take a look at this guy now. So this guy now will be here is going to be occupying that. You see that? The converting row to column, and you're also going to do the same for all. And let me also tell you this. If you take a look at the arrow here, you're actually going to see the arrow can proceed in two directions, which means if I take a transpose of A and I got that, if I also take a transpose of a transpose, like a transpose of a transpose, a transpose of a transpose is actually going to take me back to the original A. Does that make sense? And that's exactly what that guy means. So look at the dimension. And we got n by p. By the time you find the transpose, it's actually the dimension also going to change to p by n. Take note of that. Okay, so we can demonstrate this. Okay, 1759 4 by 1. Okay, and I find the transpose is actually going to be 1 by 4. Okay, and of course, if you have a matrix given as this 4 by 2, okay, taking the transpose of that is going to be 2 by 4. Okay, the transpose is just changing or converting the row to columns or columns to row. Okay, now we want to have properties associated with transpose. Okay, number one is what I wrote here the other time. The transpose of a transpose actually going to be the original matrix. Okay, and let me tell you this: if I had A to B, okay, if I had A to B, okay, A is a matrix, B is a matrix, and I find the transpose of the addition. Okay, but let me tell you this: the only way if I want to add A to B, they have to be in the same dimension, because I wanted to take note of that. Okay, matrices at different dimensions are not conformable for addition, and they are not also conformable for subtraction. Okay, so if I add this to that and I find the transpose of that, okay, mathematically speaking, is the same as as this. Okay, it's the same as that. So you can actually, if you want to practice that, you can take on two different matrices, but the matrices they must have the same dimension. Okay, and you add them up and you find the transpose of it, the same thing as that. Okay, and of course, if you have, let's say, B is a constant, you multiply a constant by a matrix, okay? And what I'm trying to talk about, maybe I have 5371, for instance. Okay, now I want to find the transpose of that. Okay, now what I'm trying to say is I'm actually going to have this transpose, okay, because constant, transpose doesn't work on constant. 2 is a constant, so transpose doesn't work, work on that. Okay. And another thing you need to know, transpose AB, okay, is the same thing. I have the transpose of that is going to be the same as this. Okay, you can see the transpose of A multiplied by B, matrices, A is a matrix, B is a matrix, is going to be B transpose A transpose, not A transpose B transpose. Okay, we also wanted to also take note of that. Now, another thing, particularly you're going to see by the time we start linear regression, okay, the transpose of an inverse. Okay, so what I'm trying to this one now, inverse, I find the transpose of an inverse, okay, is the same thing as this. Okay, it's the same thing as that. Okay, the transpose of an inverse is the same thing as inverse of a transpose. The transpose of an inverse is the same thing as inverse of a transpose. Okay, all these have been mathematically proved. Okay, all what you just need to do is to look for matrices, matrix example, then you can see how you can verify that. Okay, now we want to talk about trace. Now, this particular trace is very, very important. Okay, in image processing, okay, in image processing, where we make use of a singular value decomposition, okay, the mathematics, behind that, is what I actually want to showcase right now. Okay, if I have a square matrix A, what do I mean by a square matrix A? Okay, the numbers of rows in the matrix is the same thing as the numbers of column. I got a P by P matrix. We use this a lot in multiple linear regression. Okay, in multiple linear regression, where you have a design matrix, you expect to have, a square matrix, or, when you take a look at your variance covariance matrix, we expect the variance covariance matrix to be a square matrix as well. Okay, message you actually interested, you have in the diagonal of a variance covariance matrix, you have the variance of each variable, and you want to know the total variation. Of course, you're actually going to add the variances in the diagonal. Now, when you take a look at this right now, you take a look at what I have in the diagonal. A11, A22, A33. When I had all of that up, that is going to give me the trace. So the trace of a matrix is adding elements that you have in the diagonal. Add them up. That's what we call the trace. Okay, so take a look at that. And of course, talking about a square matrix, and example of that is this. If you take a look at this, you have a matrix A, and of course in the diagonal. Can you see that? That's what you're adding. So the trace of that matrix is actually going to be 18. Okay? Now, let me tell you this. Those who I found out when I was doing my PhD, if you are doing a PhD program in a mathematical related subject, what could be a serious issue is your mathematical knowledge. So if I took my time, to have a revision on mathematics, like particularly the linear algebra, and let me tell you this, uh, whether even in calculus, there's algebra in calculus, there's algebra everywhere, and of course, if you want to put into, maybe you want to develop statistical models, of course, you need the knowledge of algebra. And that's why we're doing all of this. So very crucial. Okay, so I'm actually want to go into matrix or trace property. The other time I show you the inverse property, but right now I want to go into trace property. The trace of A, okay, is going to be equal to the trace of A complement. Don't forget, okay, when you are rearranging element in A to get the transpose, okay, you're actually going to see that does not really change what is in the diagonal. even though the position of what element in the diagonal change, but does not necessarily change what is in the diagonal. So the trace of a matrix A is going to be equal to the trace of the transpose of that particular matrix. And of course, if I had two matrices together, I find the trace of that is the same thing as the sum of respective, trace of the matrix. Then the trace B, where B is a constant, okay, it's going to be B a constant multiplied by trace A. You can bring a constant out, okay. Then the trace AB is the same thing as trace BA. Now, let me tell you this. At times, AB, even if AB, okay, even if AB, okay, we know in matrix, AB may not necessarily, AB may not equal to BA, okay, AB may not, because commutativity don't work, okay, except if all the elements are the same, okay. But right now, okay, irrespective of this, the trace, okay, the trace of AB is the same thing as the trace of BA. Okay, and of course, if A is symmetric, okay, the trace of A, which is going to be the sum of lambda, we're actually going to make use of this when we're working on principal component analysis, okay, where we're going to be talking about the eigenvalue, the eigenvectors, and so on like that. Now, but if you take a look, if I have a matrix A and A is symmetric, what do we mean by a symmetric matrix? Okay, let me award an extra credit now. Award an extra credit now. Well, what do we mean by symmetric matrix A? Can somebody tell me? What makes a matrix to be symmetric? Okay, go ahead.
Other than the diagonals, the numbers would match up if it's transposed.
Okay, what's equal to the transpose?
The transpose is when you take the matrix and basically the leftmost column would become the topmost row, and then you just repeat that all the way down.
Okay, so are you trying to say the transpose, the original matrix equal to the transpose?
Yeah.
Is that what you mean?
That would be symmetric matrix, yeah.
That would be what? Symmetric. It's asymmetric or symmetric. I just want to.
Asymmetric or symmetric? What are you?
No, I mean symmetric. Like, yeah, that's what I mean. Look at that. Yeah, this one. That's what I mean.
Yeah.
So, are you trying to say when the matrix equal to the transpose of a matrix that make it symmetric? Is that what you mean?
Yes.
Okay. Any other person? Want to say something? What make a matrix to be a symmetric? Like, for instance, I asked you to investigate. Maybe I give you a matrix and say, okay, investigate whether this matrix is symmetric. So, what make a matrix to be symmetric? What make a matrix to be symmetric? Okay, send me a message for extra credit. Okay, now let me tell you this. That trace A equal to summation of lambda j, where lambda j is the jet eigenvalue of A, that only apply to situation where A is symmetric. Now, if you have a square matrix is actually saying the numbers of rows and columns are the same. Now, we actually get some matrices where when you find the transpose of the matrix, you're still going to have, the original, the way it was. Now, but I'm going to show you all of these. Okay. Now, take a look at this. This is what it's trying to say the other time. So don't forget to send me a message for extra credit. Look at that. A equal to A transpose. That's what we mean by symmetric. Okay? When I actually have a matrix A and I find a transpose and nothing change after finding the transpose, then that is said to be symmetric. Okay? Okay, so that's what I mean. And I'm going to give you an example now. Let's take a look at matrix A equal to that, 4 by 4, right? And let's see whether this is symmetric or not. It is not, because you can see that 3, right? So the entire the matrix that we have is not exactly the same as the original. Okay? After converting the row to column or column to row, they have to be the same to be symmetric. Now, the diagonal now. You know, let me tell you this. When you have a matrix and off diagonal is 0, 0, 0, 0. Off diagonal is 0, 0, 0. And you only have numbers here. And all the numbers that you have in the diagonal, they are not all zeros. Even though some can be 0, that's no problem. But in the case of variance, it's not going to be 0. Does that make sense? Okay, so this is a diagonal matrix. And let me also say this. A diagonal matrix has to be a square matrix. You can say I have P by P. It has to be a square matrix. Okay. Now, we're going to talk about identity matrix. What is it? There's something I wanted to say. If you look at identity matrix, if you look at the diagonal matrix, okay, I'm actually going to say an identity matrix, a special form of a diagonal matrix. You get identity matrix, when all the elements in the diagonal matrix is 1, 1, 1, 1. Does that make sense? If you take a look at this now, this is a special form of a diagonal matrix. A special form. Okay? So take a look at that. It's also a square matrix. Okay. We can also have matrices of zeros. Okay? We can have vectors of zeros. There's a particular distribution in statistics that we call standard normal distribution. Has anybody heard about standard normal distribution before? Okay, thank you so much. Now, if X followed normal with this, okay, and f of X is this, okay, where X lies between this and this, of course, we can say Z follow normal with this, and f of Z equals. Okay, if you take a look at this is a standard normal distribution when the focus is on univariate. But when the focus is on multivariate, I want to talk about multivariate standard normal distribution. I'm actually going to, and the mean, here mean is 0 for, for just one variable. If I have so many variables, I'm going to have 0, 0, 0, 0, and that's exactly here. Take a look at that. Okay, you see that? That is zeros, vectors of zeros. Okay, by the time we start multivariate normal, we're going to make use of that. Now, and this is zeros in matrices, where all the entries zeros. And here, ones. Okay, take a look at that. And here, ones. Okay, so take a look at that. All of that have application. Like for instance here, 1 is the mean. If Z is multivariate in nature, then I'm going to have several means. Okay, so we can have 0 matrix, 0 vector. We can have 1 matrix, 1 vectors. That exactly. Okay, now what I want to do now is to go into basic calculations. Okay, I want to go into basic calculations. And what we're going to do in the basic calculation, matrix equality, matrix addition, subtraction, vector product, matrix product. Take a look at this. I'm going to start with this. If I were you, try to revise your try to do revision on this. I have A to be that and B to be that. Okay. If you take a look at A and B, all the elements in A is the same as as the element in B, then I can, authoritatively write A equal to B. Okay, because all the elements in the matrix, they are all equal. And if you take a look at the second one, okay, even every others are equal, but except one. If you can identify, if you take a look at here, 9 here, 0 here, of course, the two matrices are not the same. With only just one, okay, with one conflict is enough to nullify equality. Does that make sense? Okay. Now we can actually perform algebraic operation on two matrices. When I talk about algebraic operation, do we want to add them up or do we want to subtract them? Okay, so if you take a look at this now, I have A and B. Of course, subtracting them, adding them, the two matrices have to be in the same dimension if you want to perform the operation of addition and subtraction. And the way we add them, we're only going to add element in the corresponding position. And as for subtracting, we're also going to subtract element in the corresponding positions. Okay, very easy to add, very easy to subtract. Okay, now we want to talk about vector inner products. Let me tell you this. We're actually going to have a product of vectors. We're also going to have a product of matrices. A product of vector is inner product of vector, very useful when you are trying to figure out the parameters in a linear regression. By the time we get into multivariate linear regression, you're going to see that we're going to make it something like this. I have a vector x, okay, and I have a vector y, okay. So if you take a look at that, I want to do s prime multiplied by y. The s prime has been given to be a row vector, right? Okay, and y prime given a row vector. If I want to do x prime y, then I will need that y is actually going to be, so y is going to be y transpose of that transpose, because the transpose of the y, you already have that. So by the time you are multiplying a vector by another vector, the way we actually gonna go, x multiplied by y1, x2 multiplied by y2 until you get to yn multiplied by yn. So you're actually gonna have something. You're actually gonna have something that look like this: xy, y1, x2, y2, until you get to xn, yn, that we can actually write in short form. Okay, so we can write that in short form. I start from 1 to n, xi, yi. Okay, and of course, and if you want to do that, there's going to be a condition. They must be in the same length. If they are not in the same length, that multiplication is not going to be defined. Okay, now this is an example. You see that finally I got 7. This is going to give you a scalar. When you do that at the end of the day, you're going to have a scalar, like I have a 7 now. What you're going to have is not going to be a vector anymore. So take note of that. Okay, now we want to talk about vector outer products. Okay, vector outer products. Okay, if you there's something I want you to take notes. Here, I want to do x, y prime. Initially, it was x prime y. X prime y led to constant answer, a scalar answer, but x y prime is actually going to lead to a matrices. Now, x, this is x, a column, because here you've been given, okay? Now, multiply by that. Now, this is going to be a different ball game, okay? I want you to take a look at this, the first row here. You use x1 to multiply everything first. X1 to multiply 1, x1 to multiply y2 until you get to, you follow first. It's only when you are done with x1, you go to x2, you all the way to xn, then you're actually going to have that. I'm going to give you an example right now. This is an example. I want to confirm to you there's going to be a lot of computation in exam. Computation. Okay? A lot of computation. Now take a look at this. At the end of the day, that's all we have. Okay? And you know, I can even know the dimension of matrix that I'm actually going to have from this. Okay? The first one, 4 by 1. I want to use 4 by 1 to multiply 1 by 4. Okay? This is row, column. The number of column of the one that I want to use to multiply must be equal to the numbers of row of the other. If they are equal, then the new matrix that I'm going to get will be 4 by 4. And that's why you have 4 by 4. Okay? So please take note of that. Okay, so matrix scalar products. The moment you hear scalar, they actually want to use a constant number to multiply a matrix. Here, A is a matrix, B is actually a scalar. Okay, so you can see B repeated, right? Because B is a constant, it can actually multiply all the every element in the matrix. This is an example. I have a matrix A. Okay, I got a matrix A now. And B is a constant equal to 2. I can use 2 to multiply every element inside that. And when I do that, I'm actually going to end up getting this. It's going to be an easy computation. Okay, now what about matrix vector product? Okay, matrix vector product. That's a product you actually want to multiply a matrix and a vector. I've shown you how to do vector by vector, but right now we want to do a matrix by a vector. Okay, now you have a matrix A is n by p. Okay, and you have a vector. Okay, if you take a look at this vector, it's actually p by 1. Okay, we have p rows, 1 column. Okay, now I told you something the other time. If you can have a sense of what the dimension of the new matrix is going to be before you even begin the operation. Okay, the first one is n by p. The second one is p by 1 row, column. And the law of multiplication said the number of column of a matrix that I want to use to multiply the other must equal to the numbers of row of the other. So if they are equal, then the new matrix, the dimension of the new matrix is going to be n by 1. Does that make sense? You can even know even before you go into the multiplication. And that is exactly what you're seeing here. Finally, you can see the dimension is actually n by 1. And the way that work is that the length S must match the numbers of columns of A. Okay, and if you take a look at what I have here, okay, if you take a look at what I have here, you're actually going to see A1, multiply, by that. So which means, okay, you actually go this way. You're going that way. Row multiply by column. Okay, row multiply by column, you get the first one, another row multiply by column, and so on like that, and you're actually gonna get the last one. So what you have, we've already written that in short form. That was why you see summation of that. Now in application, if A equal to that and S equal to that, if you multiply, you can see what we have. Okay, please practice that. Now this is another one. Okay, this time around, matrix by matrix multiplication. We've done vector by vector. We've done vector by matrix. We are now doing matrix by matrix. It's the same thing. Okay, it's the same thing. But take notice that AB is now equal to BA. Now, it's an example. That's an example. If you take a look at that. Okay, that's an example. You're going to see that you four of us use this. Okay, on this, you can see that row goes to column, and that will give you this one here first. Then you use that same guy on the second row, that will give you this one. Then before you now proceed to go to the next row and you repeat the same. Okay, now lastly, this is the last page. Multiplying by identity matrix. Okay, of course, if I multiply a matrix, identity is more or less like 1. Okay, if I multiply a matrix by an identity, I'm actually going to have the matrix back. Now, all of these, they are very, very essential. Okay, when we're trying to analyze, multivariate data. Okay, so what we're going to do next is actually, now today we've done a matrix, the basic definition, the basic calculations. But what we're going to do on Wednesday is, if I have a matrix, okay, how can we decompose the matrix? And after decomposing the matrix, what is our intention in real life application? Okay, we don't just do what we do. There's a reason why we do what we do. Is there any question before I go today? Now, materials for Wednesday and materials for Friday have already been uploaded, and I've also uploaded assignment 1. Okay, go ahead.
I noticed that we're doing a lot of R code in homework 1. Is there a part in the textbook you want us to look in to learn how to do that, to learn how to use that R code?
Okay, that's a very good question. Yeah, even though there's no lab for this class, we believe that. So what I'm going to do, I will make a suggestion today on Canvas about, I think I will upload maybe our material. Okay, so I will do that so that can help you, because we can't do multivariate analysis without software, because imagine you're working with voluminous amount of data. Doing it manually is going to take a lot of time and may not even be visible. I will do that. Yeah.
Do you have a preferred file format for the upload?
Prefer file for upload. I normally prefer PDF.
Can I use HTML is okay?
Provided
It's the same thing.
it's the same thing. Yeah, that should work. Yeah. Okay. Bye for now, everyone.
I'm gonna go get my. Yeah, I never know about work. So all of my classes are HTML.
Yeah. Oh yeah, actually. Yeah. I mean, I have it installed right now, but I just like HTML better. I can you knitted this over and over and over again without having to worry about flipping the PDF file?
What I did was really, like, I opened the HTML in a web browser and I, like, control-C created a
Oh, yes, there you go. Easy.
That was my work name.
Yeah. What's your name? I'm calling. Are you staff speaker?
No, it's fine.
Hey, high five! Right on. Are you getting undergrad or math? Okay, I'm doing my math.
Well, what did you study?
My first bachelor's was in supply chain management, but I didn't do enough math at the time, so I'm doing everything over again. Oh, second bachelor's in mathematics. Last semester, so I'm going to start applying for jobs here next month. Thank you. Thank you very much.
I'm trying. Red light.
Yeah.